Okay, so good afternoon and welcome to lecture number 27. So in today's lecture, we will study recognition as a graph basically. This is a part of syntactic object recognition. So particularly we will study syntactic classifier and then how recognition as a graph matching is done, and then at the end how matching is similarity is found by using length and distance. So that we are going to study in today's lecture. Yesterday we talked about this one, syntactic object recognition. In that we studied the difference, and then what is my grammar, what is my language, and all those things we have studied in yesterday's talk. And today we'll study the last part of this chapter, that is the recognition as a graph matching, in which first we'll study syntactic classifier, and then how graph matching is done, so graph isomorphism and so on. So there is one algorithm which is available, so that we will study that one, and at the end how similarity is found by using length and distance. So this is today's agenda. Yesterday we talked about the grammar and this one language and so on. So you know that this grammar is defined as a floor tuple. So floor tuples are, that is Vn is nothing but the finite set of non-terminal symbols or variables that represent the intermediate construction. Vt is nothing but the terminal symbols, or it is called as the structural primitives, and so on. So and then P is nothing but the production rules. As I said, that production rules for every class will be different, and S is nothing but the starting point, where to start. So the S is nothing but the grammar axiom or the start of the start symbol. So like that way, this grammar consists of tuples. So all those information will be available in that. And a language, as I said, that for every class, there will be a separate language. So if you are doing in a supervised learning approach, so first you have to develop the language of every class, and then when unknown pattern comes, you have to apply the set of rules of class 1 and see whether you are getting the language like as a class 1. If not, then apply set of rules or grammar to this unknown pattern and see for class 2 and so on. So like that way you have to go ahead, and then wherever you get the matching, that unknown pattern will be assigned to that one. So language we have seen yesterday, and also we talked about the two class problem, that is C0 and C1 means let us consider C0 and C1 are the two classes represented as strings of primitives, and strings of primitive is nothing but the language of that class. And suppose there are two grammars like as a G0 and G1. So G0 is a grammar for C0 and G1 is grammar for C1. And then production rules are such that G0 allows generation of sentences which corresponds to the object of only class C0. So from this G0 we will consider the language of C0, and then from C1 we will generate the language of C1. So language of G0 generated by grammar G0 is of the class C0, and similarly the language of G1, language of Z1 is the language of class C1, right? So also we talked about yesterday, up to this point we have studied that once Z0 and G1 have been established, what is the next this one? In general, a class of object may be defined by more than one grammar, and when there are more classes, the syntactic classification approach is same, so except more grammar involved in the process. So see, suppose for example here given a sequence of primitives representing an unknown pattern. So this is the query pattern, and then what we are doing, we first we'll apply the grammar of G0, and then we'll see whether we are getting the language of this unknown pattern like as a language of G0. If yes, then that pattern will be assigned to the class C0. If not, then we'll apply the set of grammars or production rules to of Z1 to the unknown pattern, and then we'll see whether the language generated by application of set of rules of class C1 is similar to this one unknown pattern. If it is similar, then we'll assign to class that unknown pattern to class C1 and so on. If not, then that pattern will be rejected. Means okay, that pattern neither belongs to class C0 nor belong to class C1. So like that way, syntactic classifier works. Okay. Now we'll see the syntactic analysis, syntactic classifier, and syntactic classifier. So if appropriate grammar exists that can be used for representation of all patterns in their classes, the last step is to design the syntactic classifier which assigns the pattern or word to an appropriate class. So construct a separate grammar for each class. So that is what we have I told you. Okay. Then decision of whether or not the word can be generated by a particular grammar is made during the syntactic analysis. Okay. So if the language is finite, the syntactic classifier can search for a match between the word being analyzed and all the words of the languages. Means what is done? We are applying this one grammar of every class, so one by one, and then we or the unknown pattern, and then we will find the match between. If it is matching, then okay, that unknown pattern will be assigned to that particular class. Otherwise, okay, it does not belongs to any of the class of the database, and so on. So syntactic analysis is based on the efforts to construct the tested pattern by the application of some appropriate sequence of substitution rules to start the symbol. Okay, and if the substitution process is successful, means when if you get, like for example, unknown pattern is there and there are two classes, so we have a separate grammar for class 1 that is called as the G0. Okay, class 2 is okay, C1. So C0 and C1 are the two classes. So G0 is a grammar, okay, this one associated with class C0, and G1 is the grammar associated with class C1, and then basically what we'll apply the grammar or production rules of class C0 to the unknown pattern, and then we'll see what kind of sequence or language we get by application of the grammar or production rules to the unknown pattern. If it is matching with language of C0, then we'll assign to that one. If not, then again we'll try it with grammar of C1, that is the G1 or set of production rules, and then we'll try to generate this one language of that class. Okay, and then again we'll compare it with the language of C1. So and in that you have to do the substitution, means you have to apply the rules, production rules, to get that particular word or language. So if the substitution process is successful, means you get, if you get the language of unknown pattern similar to the language of this one, that class, then we can say it is a successful. The analysis process stops and the tested pattern can be generated by the grammar. Okay, and the pattern can be classified into the class represented by the grammar at that time. So if the substitution process is unsuccessful, as I told you that if, like for example, we have applied the grammar of class C0, which is nothing but G0, to the unknown pattern, and then application of grammar or production rules to the unknown pattern, at the end, if you don't get the language of unknown pattern similar to the language of class C0, then it will say that it is unsuccessful. Okay, so if the substitution process is unsuccessful, the pattern is not accepted as representing an object of this class. Okay, then what you have to do? Then you have to apply for the second, and so on. So syntactic analysis can be done in a top-down manner or in a bottom-up approach. So in top-down manner means basically, okay, see that there is a difference between a top-down approach and bottom-up approach. So see that for every class you get a particular language. Okay, for if there are 10 classes, so you'll get the 10 languages. Every class will be represented by one language, right? So in the top, so this, okay, Top-down approach means basically you have to begin with the start symbol, and substitution the rules are applied in an appropriate way to obtain the same pattern word as that under analysis. Like means what happens basically, see that you know the language of class C0, you know the this one production rules or grammar of class C0, right? Now you are applying this grammar to the unknown pattern one by one, and then finally what you get basically the pattern similar to the this one language, or at the end what is the result, you get basically the language of unknown pattern similar to the language if that unknown pattern belongs to class C0. If not, then you'll get the different language. Then you can say that this unknown pattern does not belong to this one. So you're starting with the start symbol, and you're trying to get the language of unknown pattern similar to the language of class C0 if you're applying the grammar of C0. But unfortunately, by application of all those grammar or production rules, if you don't get, then you have to take the decision that unknown pattern does not belong to class C0, right? So you are starting with a start symbol. So begin with the start symbol, and you are substituting the rules, which rules of that class, and then after appropriate way application of these rules, what is the end result? End result is that expected result is that the language of unknown pattern should be same as a language of known pattern, okay, whose grammar is applied to the unknown pattern. If they are similar, if they are not similar, then what will happen? Even if you apply the rules of that known pattern, then even application you will not get the same kind of language. So here top-down approach is nothing but begin with the start symbol, and substitution rules are applied in the appropriate way to obtain the same pattern word as under analysis. So this is top-down approach. Whereas a bottom-up approach is exactly opposite, means you know the language, and then start with the analyzed word, which is reduced by applying the reverse substitution. And okay, see that in a reverse way you are applying in bottom-up approach, and what you will get, see that here you get the language. Here what you will get after application of the reverse way, you will get the symbol S finally. So final goal is to reduce the word, means here you know the language, and then you are applying the substitution of rules, and then okay, finally what you should get, if that object belongs to that class, finally you will get the start symbol, okay, at the end. Whereas here in top-down approach, final goal is to generate the word as analyzed word, like as a language of that class, and so on. So here you are beginning with the start symbol and ending with the language of that class. Here in bottom-up approach, you are beginning with the language of that class and ending with the start symbol. So here you are applying all the rules, production rules, in a reverse way. Here you are applying all the production rules in a forward way, and so on. So this is the way you can do the syntactic analysis by either top-down approach or bottom-up approach. So here in bottom-up approach, you should have the language of that unknown pattern known. Here, even if you don't have, then you can do it with this one top-down. So mostly this top-down approach is used, right? Now, recognition as a graph. Like for example, you have developed the graph of known patterns graph is there, and unknown pattern graph is also there. Okay, so you'd like to know whether this unknown pattern belongs to class C0 or C1 or Cn, and so on. So you have the graphs. Now, how you can say that this graph is similar to this graph, or this unknown pattern belongs to class C0 or C1 or Cn by using graph matching technique? So you know that in a graph theory, Z is defined as an ordered triplet of V of Z, E of Z, and Psi of Z. Now, what is V of Z? V of Z is nothing but the non-empty set of vertices. V means vertices, E means edges. Okay, you know that graph consists of vertices and edges. and then psi is nothing but the incident function, means okay, between two vertices which edge is there, so it will give the information about it, right? So psi of z, see, v of z is nothing but the non-empty set of vertices, e of z is nothing but the set of edges that is disjoint from v of z, and psi of z is the incident function which associates with each edge from E of z, an ordered pair of vertices from V of z. If there exists an edge E belongs to E of z between two vertices U and V, where U, comma V belongs to E of z, then psi of psi z of E equal to UV. Right? So this will be more clear from the next example. How do we find the V of z, set of V of z? How do you find the E of z? And how do you find the psi of z from the given graph? So in a graph, basically, it is an ordered triplet, okay, which consists of V of z, that is nothing but the vertices, set of vertices. E of z is nothing but the set of edges, and psi of z is the incident function. Now we'll take one example and we'll see how to find out this V of z, E of z, and psi of z from the graph. Now see that, suppose for example this kind of figure is there, pentagon kind of figure is there. So this is first node V1, second node V2, third node V3, fourth node V4, fifth node V5. Now between V1 and V2, there is a edge E1. Okay, so E1 is nothing but the first edge, which is in between V1 and V2. E2 is the edge between V2 and V3. Similarly, E3 is from V3 to V4 and so on. Between V3 to V5, E7 is there, and then V4 to V2, E6 edge is there. So in total, there are 5 vertices, V1, V2, V3, V4, V5. 5 vertices are there. And how many edges are there? 7. E1, E2, E3, E4, E5, E6, and E7. So what is the set of V of z? So V is basically a set of vertices. So how many vertices are there? 5 vertices are there. So V1, V2, V3, V4, V5 is nothing but the set of V of z, right? And then E of z is basically a set of edges. How many edges are there? 7 edges are there. So E1, E2, E3, E4, E5, right? So E1 and E6 and E7. So E of z is nothing but the set of edges, right? Now the incident function of E1, okay? So E1 is, okay, where is E1? E1 is in between V1 and V2. So this one, psi of z, E1, psi z of E1 is nothing but this is the edge between V1 and V2. Okay, so E1 is the edge between V1 and V2. Similarly, psi z of E2, so E2 is in between V2 and V3, and so you can find psi z of E3 will be between V3 and V4, and so on. Similarly, psi z of E7 is nothing but V3 and V5. So you got all those basically sets from the graph. Now, if you know the V of z, if you know the E of z, and if you know this incident function of this known patterns as well as unknown pattern, then how do you find okay, graph matching, or how do you find, or how do you classify that unknown pattern? Okay. Whether it belongs to class C0 or C1 or something like. Okay, means basically you know the these 3 sets of all the classes. Okay, and then similarly you will be finding this one, these 3 sets of unknown pattern, and then you can find, okay, you can find the matching between the graph, okay, these sets and the unknown patterns and so on for every thing, right? So for finding the similarity between 2 graphs, okay, graph isomorphism is used. So what is graph isomorphism? Suppose for example there are 2 graphs. G1 is one graph, okay, which belongs to class C1, and G2 is another graph which belongs to class C2. Okay, so two graphs G1 and G2 are said to be identical. When we can say that this graph and this graph G1 and G2 are identical, if number of vertices, see that vertices of G1 is equal to vertices of G2, right? If number of vertices of graph G1 and number of vertices of graph G2 are equal, that is first thing. Okay. Second thing is that this one E of G1 must be equal to E of G2, means edges, number of edges of G1 must be equal to number of edges of G2. Okay. Now, third thing is that incident function must be same of graph G1 and G2. So psi of G1 must be equal to psi of G2. Then we can say that graph G1 and G2 is identical. So two identical graphs can be represented by identical diagram. Now, so graph isomorphism algorithm is there. Okay. So we have to take the two graphs, the G1, which consist of first initially this one V1 and V2, V1 and E1. Okay, vertices of graph 1 and E1 is nothing but the edges of graph. Okay, 1 and G2 is vertices of graph 2 and E2 edges of graph 2. So use the node property criteria to generate the subset V1I and V2I of the node set V1 and V2 and test whether the cardinality condition holds for the corresponding subset. So if not, the isomorphism is disproved. Now, what is my cardinality condition? Cardinality condition means basically, okay, number of nodes of first graph must be equal to number of nodes of second graph. Second thing is that number of edges of first graph must be equal to number of edges of second graph. So this is the cardinality condition. First condition must be satisfied to say that two graphs are same or identical. If this does not hold, then okay, there itself we can say that these two graphs are not similar. So sometimes it may happen that object is rotated, or you are basically this one edges which are given the name, okay, like E1, E2, E3, E4. So they are different. Like for example, instead of E1 here, okay, if somebody says that okay, instead of E1 here, somebody says that it is E7, and then E1 is somewhere. Then what will happen between the first, basically in this diagram, what is the size Z E1? That is V1, E2, V1, V2 now. But okay, in other graph, if this is E7, then what will happen? Size E7 will be equal to V1, V2, whereas here in this graph, this is V3, V5. So basically their incident function will not match because of different labeling and so on. So first thing is that in a this one, sorry, in a graph isomorphism, first you have to test the cardinality condition. So cardinality condition means number of vertices of graph 1 must be equal to number of vertices of graph 2. Number of edges of graph 1 must be equal to number of edges of graph 2. If this holds, this is called as the cardinality condition, then we can say that there is a possibility that these two graphs are equivalent. Okay. Then what you have to do? After that, for unknown pattern, you have to label the nodes of each of the graph with labels 1 to p, right? So nodes are labeled as a 1 to p, and then you have to form the adjacency matrix for each graph. Okay, form an adjacency matrix for each graph and call this as a M1 and M2 respectively. So adjacency matrix for each graph, M1 for graph 1 and M2 for graph 2. Okay. And if M1 and M2 is same, okay, adjacency matrix is same, then graph Z1 and Z2 are called as an isomorphic graph, means they are similar. But suppose, for example, you have the this one adjacency matrix of graph Z1 is M1, and which is not similar because Z2 labeling is something different, and because of that, adjacency matrix entries will be different, and you will find that these two graphs or adjacency matrix are not similar. So in that case, what you have to do? You have to change the labeling of graph 2, okay, and then again you have to match. So how many times you will change that one? So that will be equal to number of this one vertices factorial. Like for example, if that this one 5 vertices are there, so 5 factorial times you have to do that one, and that's why complexity increases with the nodes and edges. This is the disadvantage of graph isomorphism. Okay, I hope that you have understood this algorithm. I'll repeat it again. Okay, see that two graphs, Z1 graph is there, Z2 graph is there. Now these two graphs, when we can say that they are isomorphic, okay, isomorphism, okay, are isomorphic. First thing is that we have to test the cardinality condition. Cardinality condition means number of vertices of graph 1 and number of vertices of graph 2 must be same. Second condition of cardinality is that number of edges in the graph 1 and number of edges in the graph 2 must be same. If this holds, then we can say that cardinality condition holds, and then there is a possibility that these two graphs are isomorphic. Okay, but okay, we have not concluded that they are okay isomorphic. There is a possibility. Then what you have to do to find out the isomorphic, next or third step is that you have to label graph 2 or unknown pattern with nodes like okay, each node like as a 1, 2, p nodes are there. So you have to label that one, and then you have to find out the adjacency matrix. So adjacency matrix you have to find for graph 1 as well as graph 2. And if this labeling is correct, okay, then this okay adjacency matrix of this one called M1 and M2 will be same for graph 1 and graph 2. And if it is same, M1 and M2 is same, then we can say that these two graphs are isomorphic, or they are identical, or they are same. If not, then what you have to do? You have to change the labeling of the nodes. And because of this labeling, incident function will change. And then again, you have to find out the this one incident matrix, adjacency matrix for graph 2, and then again you have to match it. Okay, so sometimes suppose for example in second iteration it does not match, again in third iteration you have to change the labels. So how many times you have to change the label? P factorial times, because number of nodes are p. So if number of nodes are more, then this will increase the computation complexity, and okay, this will increase the complexity. And if suppose for example after doing all those things, if adjacency matrix does not is not same, then we can say that graph 1 and graph 2 is not isomorphic, right? So unknown pattern does not belongs to class C1 or something like that. I hope that you have understood this one. Now, similarity of graphs. So all the approaches considered earlier for perfect match between the graph are not. So here what we are doing, we are finding the perfect match, right? So all the approaches considered earlier for perfect match between the graphs are not able to distinguish between small mismatch or very similar graph. Like for example, there may be a similar graph or small mismatch or which looks like same, but here in earlier graph isomorphic method or graph isomorphism, you have to match it exactly. Then we can say that this unknown object belongs to that class. So there might be chances that there may be very similar or small mismatch may be there, and in that case, your algorithm will say that okay, this does not belong to that class. So to avoid that one, okay, another method is used, and the similarity of two strings, like as a language, can be based on the Levantine distance. So for example, class C1 is having language L of Z1, and class C2 is having language of L of Z2, right? Now, when we can say this this object and this object in syntactic classifier is same, if the language of this one is same, or like for example, similarity. If suppose for example there is 5 letters are there or 5 symbols are there, and then there are only 4 symbols are there. So one symbol, if you delete from this one, so there will how many will remain? 4. Here also 4. And if they are same, then we can say that this object is similar to that. Not exactly same, but it is similar, because okay, by deleting one symbol or one this one primitive, you get the language of this class like as this class. Okay, so either you have to delete, or we have to insert, or you have to substitute to convert one string into another. So this is done with the help of length and distance. Okay, we can measure the length and distance. So every operation, deletion or insertion or substitution, okay, it will cost a unit. Okay, in length and distance, this one, finding the distance. So transformation of strings element can be assigned a specific transition cost. So this is cost we have to calculate to make the computed similarity, that is distance, more flexible and more sensitive. Now, how it is done, let us take with one example in my next slide. So this principle can be applied to find the graph similarity as well. So the set of feasible transformation of nodes and arcs, that is insertion, substitution, relabeling, is defined, and these transformations are accompanied by the transition cost. Okay, so any sequence of transformation is assigned a combination of single step cost. Means if I delete one symbol, I'll consider that as one cost, or if I insert one symbol, I'll consider it as one unit cost, and so on. So if there are, suppose for example, 2 deletion and 1 insertion, so 2 deletion will cost 2 unit and 1 insertion will cost 1 unit. So distance between that one will be 3 unit. And if that, suppose for example, if there is only one this one deletion and 1 insertion, there will be 2 unit cost, like that way. So any sequence of transformation is assigned a combination of single step cost, and the set of transformation that has the minimum cost, like for example, and it transforms one graph to another graph, defines the distance between them. So definitely when we can say the this graph is similar to this graph, if this graph is having minimum distance of minimum length and distance, then we can say that this graph belongs to, or this graph is similar to this graph. Okay, or like for example, there are 4 graphs and then unknown pattern is like this one, unknown pattern is this one. What we'll do, we'll try to find out the similarity between this one and all those 4. So wherever you get the minimum cost of unknown with this known this one, then that unknown will be assigned to that class where you'll get the minimum cost. Right now, this example will clear you okay, to find out the distance or find out the similarity between the languages of 2 class. Suppose for example, this S1 is the language. Okay, S1 is one class, S2 is another class, S3 is third class, and S4 is 4th class. Now we can find, okay, whether this S1 and S2, okay, what is this length and distance between S1 and S2? So what is the language of S1 class? This is A, B, A, D, C, D, E, F, A, C, D, E. So this is the language of S1 class, whereas language of S2 class is A, B, A, D, 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 E, F, A, C, D, E. So this is the language of S2 class. Now we'll find, okay, the similarity between this one S1 class and S2 class by using length and distance. Okay, so see that this is the language of this class, S1 class, and this is the language of S2 class. So where is the difference? See that here A is there, here is also A. So A, B, B, A, D, C, or D, D. Only change is that in S1 class, this is C, whereas in S2 class, this is D. Okay, the next one is D here, here also D, then E, F, A, C, D, all those things are same. Now what we have to do, when we can say, okay, what is the distance between S1 class and S2, or length and distance, what you have to do, you have to delete D here, right? You have to delete D, and what you have to insert? You have to insert C. Okay, if you delete this D and insert C, so deletion will cost 1 and insertion will cost 1. So how many operations we are doing? Deletion of D and insertion of C here, so that the language of this S1 class and language of S2 class will be same. So how much is the distance? Distance will be equal to 2. So the cost will be equal to 2. Why? Deletion and insertion each will cost 1. So D we are deleting first, and then we are inserting C. So deletion will cost 1 and insertion will cost another 1. So in total cost will be equal to 2 unit, and then this language and this language will become same. So distance, length and distance between S1 and S2 is 2, right? Similarly, you can find out the length and distance between S1 and S3. Okay, so see that A is there, A is there, B is there, B is there, A is there, then D is there, D is there. Okay, now here, see that here it is C, but here it is E. So what you have to do, you have to basically insert C. Okay, again D is not there, you have to insert D, and then E is there, F is there, A is there, then C is there here, right? But there is one more C, so you have to delete this C, and then D and E. So how many costs are there? For insertion of this one, CD here, C, one cost, D, another cost, and then here for deletion of this C, there will be three costs. So what is the length and distance between S1 and S3? It is 3 unit. What is the length and distance between S1 and S2? It is 2 unit. Okay, so this S2 is more close to S1 than S3 because this is having 2 unit distance, whereas this is having 3 unit distance, right? So okay, by insertion of this CD and by deletion of C, so this language will become the language like as a S1. So this will cost 3 unit and this will cost only 2 unit. So that's why S2 is more similar to S1 as compared to S3. Similarly, you can find out the distance between S1 and S4, and then you can, out of that, this one, S2, S3, S4, which one is more similar to S1 you can find. So in this way, this one, in syntactic classifier, distance is measured, and then we can find out the similarity of the object and so on. I hope that you have understood the syntactic classifier. So this finishes our chapter number 4. In the next lecture, we will start our dynamic scene analysis. So see you on Monday. So thank you very much.